Hello students, thank you for joining us. This is the lesson on section 6.3, apparent forces in circular motion. And what we're going to do is we're going to be talking about things that are traveling in a circle. So that circle could be horizontally oriented or it could be vertically oriented. In reality, it could be at pretty much any angle in between those. But this is high school physics, and so we're going to be talking about just these two sort of basic scenarios, something where maybe it's rotating like this or rotating like that. So one of the situations where this occurs is, that's kind of fun to talk about, is in roller coasters. We've already talked about that at all points, if you're traveling in a circle, that the velocity vector is tangent to the circle. The acceleration is pointing towards the center, so therefore the net force is pointing towards the center. We talked before about the value of that acceleration. We talked about how that the force is not a new force. It's called the centripetal force, but it is going to be caused by one of the existing forces that we're already aware of, such as tension, normal force, maybe just some external force. My hand could be pushing something slowly around in a circle, or what have you. There's an interesting phenomenon when you look at, when you think about something going around in a circle. It could be going really fast. So if you had, think of like maybe if you ever played with Hot Wheels, you had the Hot Wheel loop, and you could send that car really fast, and then it would come down and make the loop, and it wouldn't be a problem. But maybe you didn't push it as hard, and it came down here, and then it got maybe about partway up the circle or halfway up the loop, and then it would sort of fall off. Or you might even get it where it would go all the way up, sort of to the top, and then it would kind of fly across the side, and maybe it would land or whatever. Maybe it wouldn't. But the idea is that there's some speed that if you give it that car that speed, or if you give a roller coaster that speed or that velocity, then it will make the loop. And that speed or that velocity is called the critical speed or the critical velocity, such that if you're less than that, you won't be able to make it up and over and around. You'll fall off here early, or you'll be here, and then you'll kind of enter a free fall and smash into the other side. If you are more than that speed, if you're that critical speed or higher, then you'll make the loop no problem. If you go really fast, you're not in any danger of falling down. So a question is, what is that critical speed? And you can imagine if you were a roller coaster tycoon that was creating a loop-the-loop, you would want to make sure that the velocity of the roller coaster was higher than that critical speed. Otherwise, you might have some disgruntled passengers on your hands. They're never able to make the loop. That's sort of a best case scenario. All right, so what we're going to do is analyze the free body diagram of the object at the very bottom and then also at the top. In fact, I don't even really care about the bottom. At the bottom, you've got weight going down and you've got normal going up. That's really not that much of a surprise. What we're really interested in here is going at the top. Are we going to have enough velocity there? So what we'll think about is we'll think about that critical speed. And if you're going faster than the critical speed, then even when you're at the top, the normal force of the track is pushing you down. If you are at a value less than that critical speed, then it's not pushing you at all. In fact, you've totally broken contact with the track. But at that critical speed, where it is just that break-even point, if you will, you are in contact with the track, 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 until you're at the very topmost part. And if you were to almost zoom in on the track right there, it would be like one moment you were right here, and then you just kind of glided across and then came back into contact with the track right there, although in reality that space would be very small. So right at the very top of the circle, it's like you just sort of fly through it, and then you come immediately back in contact. But it's almost so. Just for that one very brief moment, that very topmost part, the track is not even pushing you down at all. It's just you sort of like glide horizontally. It's not the best way of thinking about it, but the idea there is that the normal force on the track, or of the track on you at the top, is equal to 0. Okay, so now right here, the normal force is going to be pushing on you. Right here, the track is going to be pushing on you. But right there at the very top, it's going to be 0. Let's go to a blank slide here, and we'll draw the free body diagram of what that looks like. So right there, when you're at the very top, the free body diagram would look like this. A moment before, the free body diagram would look like the weight is going. Actually, the weight would be going down like that, and the normal force would be perpendicular to the curvature of the surface. But at that very top moment, when you're just zooming right across the very top part, the only force acting on you is weight, which is actually kind of interesting if you think about it. Now, that's not the whole story, because as we saw a moment ago, I mean, you have a velocity. Your velocity is looking like this. So it's not like we just in the next moment the roller coaster is just going to be falling down. It's already got a trajectory, if you want to think of it like that. But the only force that's acting on it in that very topmost moment is weight. And that's helpful for us, because then we can write Newton's second law, summation of forces in the y direction. And it's not too bad. It's down, so we'll write negative weight. And that equals the mass times the acceleration in the y direction. Okay, what we're interested in is, what is that velocity? So what is the velocity at that moment? So we'll take this equation and kind of start filling out a couple things. Well, first off, we know that the weight is the mass times gravity. And the acceleration, which you are feeling, is the centripetal acceleration. And we had a formula for that. That's equal to your velocity squared divided by the radius, where the radius is the radius of the center of that circle out to you. What's interesting about this formula right here, if you look at it, is that we've got a mass on this side and a mass on this side, which means if we divide both sides by the mass, then they completely cancel each other out. So we have negative g equals v squared over r. Now, we've got a couple things we can do here. We could say that this acceleration is in the negative direction and things like that, but that's where the negative's coming through here. But we're mostly interested in that v squared. So we're going to multiply both sides by r. So we have g times r. I guess what we can do is we can go ahead and say, that the acceleration is negative. If we say that acceleration is negative, and it's negative here, then we multiply both sides by negative, and it'll go away. This is the interesting thing. So we'll take the square root there, and you end up with v equals the square root of gr. And this is known as the critical velocity. That's the velocity that you have to be traveling if you're going to come down and do a loop. At least at this moment right here at the top, you need to be the square root of 9.8 meters per second squared, if your roller coaster is on Earth, times the radius. And you take the square root of that. You need to be going that speed or faster up at the top if you want to loop the loop, as they say. All right? And if you've ever been on a loop-the-loop type roller coaster, I believe we mentioned this before, you can attest that when you're at the very top, if you have your hands up, like you should in all roller coasters, then your hands will actually feel being pressed down. Okay, because the net force is downward, because the acceleration is pointing towards the center. So the net force and the net acceleration are both pointing in the same direction. So there you go. That's the critical velocity. That's critical the critical speed square root of GR. Let's see if there's anything else that we need to talk about with this particular lesson. I don't think so. So the book did talk about some other things about the apparent forces and things that you feel, but this is the big idea here from 6.3. All right? I'll see you here in a moment when we talk about 6.4, which is orbit.